Okay, welcome everyone. My name is Chris Hauser. I'm the host for today's IFRR Robotics Global Symposium series. Today we're going to be looking at the topic of task and motion planning, and I'm very pleased to welcome today's speaker, Tomas Lozano-Perez from Massachusetts Institute of Technology. We will also be joined by front row guests, Hannah Kurniawati at Australian National University, Jingjin Yu at Rutgers University, Jan Peters at TU Darmstadt and Max Planck Institute, Steve Laval from University of Oulu, David Su from, oh no, sorry, he's not here, excuse me, and Rashid Alami from LAS. So about how this is going to go, Tomas will be fielding questions from the front row guests during his talk. And those of you who are in the audience can use the link on Slido to ask questions, and we will be going through those questions during the Q&A sessions of today's talk. So let me start by describing the problem of task and motion planning in a bit more detail. So as motion planning technology grew to greater maturity in the 2000s, researchers started looking into the problem of task and motion planning around in the 2010s. This problem is trying to integrate the problems of AI planning, which deals with symbolic knowledge and decisions in symbolic spaces, with continuous decisions that were becoming more and more mature with the advent of sampling-based planning technologies. And so if you want to build a robot that is, for example, going to build a sandwich, it of course needs to figure out how and when to schedule its manipulation actions in order to complete the sandwich, but it also needs to figure out how to move its own joints in order to be able to accomplish these actions. So task and motion planning, excuse me, emerged in the 2010s as a way to deal with bridging the gap between these two domains, this one symbolic and one continuous. So Tomas Lozano-Perez was very instrumental in developing many of the technologies behind task and motion planning, along with others such as Stuart Russell at UC Berkeley, Lydia Kavraki at Rice, Bernhard Nebel at TU Darmstadt, and also Tamim Masfour at Karlsruhe. And they've been working on essentially coming up with the foundations of task and motion planning. Now, a recent trend has been looking at how we can use learning to start to accelerate task and motion planning, because these planners will have to deal with doing tasks that are similar to planners experienced in the past. And I think that's where Tomas will be speaking a lot about in his talk today. So just as an introduction to Tomas himself, he is a professor at MIT. He is the School of Engineering professor in teaching excellence there. A couple of fun facts. He was born in Guantanamo, Cuba, and raised in Puerto Rico. And ever since he came to the US, he apparently has really enjoyed being at MIT, where he's been at the last 52 years. So not only did he do his bachelor's, master's, and PhD at MIT, but he's also been a professor there for 40 years. I've learned about his work all the way back in my graduate career, learning about motion planning. Tomas was instrumental in the development of the idea of configuration space, which is now the backbone of modern motion planning. He's also been working on manipulation problems for quite some time, as well as POMDPs, along with his longtime collaborator, Leslie Kaelbling. He's won numerous awards, including the 1985 Presidential Young Investigator Award, the 2011 Robotics Pioneer Award. He's also a fellow of AAAI, a fellow of the ACM, a fellow of the IEEE, and just all around a very charming fellow. Without further ado, I'll turn it over to Tomas.
Thank you, Chris. I guess I'll need to share the screen. Can you see that? Okay. Thank you, everyone, for attending, and especially the front row guests. And thank you, Chris, for the introduction. I'd like to amend your introduction a little bit, though, which is that as far as I'm concerned, the real birth of task and motion planning was actually before the 2010s, and it was due to Rashid Alami, who happens to be one of our front row guests. So Rashid actually I consider to be the real pioneer in this area, and I'm really honored to have him here. Thank you, Rashid, for coming. Okay, so I'm going to, the talk is split into three pieces. The first part, I'm going to focus on setting up the task and motion planning and why choose task and motion planning as a way of trying to build general purpose robots. The second part will focus on some common misconceptions about task and motion planning, and I will try to kind of address them in the context of some of the work that we've been doing. And the third part of the talk will really be about the integration of learning and task and motion planning. So that's really the kind of structure, and we'll pause in the middle to take some questions. Okay, so I've set this up here as the goal being general purpose intelligent robot because, I mean, much of robotics is not about this topic. It's really about, robots for particular applications. So it's important to have in context that what I'm talking about and is really about how to try to get some of a robot to be generally useful. And there's kind of two ways of looking at the challenge of trying to build a general purpose robot. One is domain variability. This is an example that Leslie likes to use, which is the idea of making tea in anyone's house. So if I drop you into anyone's house, pretty much anywhere, you can probably find some way to make tea. So find some some water, heat it, and put something in it, and make tea. The other thing that's important is the idea of task variability. Of course, there's economic value in having robots that can do one job very well, but I'm interested in the challenge of how do you get a robot to do a wide variety of tasks, not sequentially, not having to be trained or programmed in between, but able to decide, okay, now I have to vacuum, now I have to clean the house. So that's the kind of goal that we're trying to set up. And I want to think of this as an engineering problem. So, there's a factory that's going to produce robots, and the robots are going to go out into the world, into the different, they're going to go into their different domains, and they're going to have, different environments, and they're going to be doing multiple tasks and so on. And our job as engineers is to find a policy program to put in their heads, in the program's head, and we're going to send them out into the world. So we're going to make the distinction between what goes on in the factory and what goes on in the wild and when you send out the robot. So this will be a useful distinction that we'll want to make. And it's useful to think about the space of defined by these two axes. One is the kind of complexity of the policy due to the variety in the domain, in the environment. So on the left is a very narrow task and environment, and on the right is a kind of very very open. And the y-axis is really what the factory knows about the domain. So we can have a lot of knowledge about some domains and relatively little about others. And it's useful to think about there being interesting points in this space, a narrow task known in advance, a narrow task that's not known in advance, very broad task, and so on. So we'll be kind of walking around this space during the presentation. So one question, and one that I feel, it used to be that one could talk about, how I'm building a planning system and not motivate why one's taking that approach. But today, with the kind of growth in machine learning and so on, one has to kind of justify why do it this way. And so I'll give you at least my opinion as to why the kind of approach that we'll be following, why we're doing it this way. So remember, we're trying to construct a policy for the put in the head of the robots that we're going to send out into the world. So we have to, figure out, how we're going to do this. And I don't have any preconceived notions. Learning's okay, engineering's okay. I'm not trying to emulate humans. What we're trying to find is really what's the best approach to build robots so as to minimize the amount of work that the engineers have to do. That's really the criteria that we care about, and we'll use whatever seems to be the right way to address the problems, independent of, this is the way children do it or anything like that. It'll just be a purely engineering problem. Okay, so how could we build this policy? So one way is you can say, well, I can have a policy. Perhaps I have some structure to the policy that I know ahead of time. Like, for example, when many of the approaches in control theory, one has a parameterized class of policies in mind, and one's trying to find the parameters. Or if you're a fan of reinforcement learning, you could search the space for policies to try to map the history of observations that this robot is going to get into actions. The problem is that this search for policies is very difficult. And furthermore, it's actually very hard to generalize them, and particularly in the context of a cumulative lifetime. If you find a policy for this job and a policy for that job, how to combine them is not clear. So for this reason, I'm going to reject this particular approach to doing things. Of course, for many other tasks, it'll be fine, but we don't do it that way. The other way, you can say, okay, well, the policies, maybe those are hard to find. Maybe it's actually better to search for a Q function, an action value function. And many approaches, like reinforcement learning or in optimal control, adopt this idea. But they have many of the same issues. In particular, the Q value over the whole state space is inconceivable in a very large problem. So you can hope that the neural network representation of the policy will generalize, but in practice, I don't believe it does that much. So it limits you to problems that are fairly narrow. And also generalization is a problem as far as I'm concerned. I mean, the Q function embodies a reward, yes, and you can try to make it be goal condition, but then the state space blows up and so on. So I think it's a problem. So we're going to reject that. So we're going to move in the direction of planning. And so the idea is that there's a planner, which is a general purpose piece of software, which has certain models, which are the transition and the reward model you can think of, or, maybe you could use a policy on Q to help guide it and so on. And then you plan based on the observations. This particular setup here assumes that you're taking the observations directly and producing actions, say torque directly, and then just do replanning as a way of creating a policy. And the problem is that this is this is really not that helpful. Just putting a planner, but operating in the raw input and action space is still problematic. It's problematic because it's difficult to learn or construct those policies, especially when the horizon is long. And it's also held to generalize. It becomes too dependent on the environment, on the training data, and so on. So we're going to reject that particular approach. And we're going to start introducing abstraction. And that's going to be the kind of main theme of the talk, is the idea that we're going to abstract away from the raw observations and the raw control, and create in our architecture a module whose job it is to take the stream of perceptions and construct a state description. And it could be there could be uncertainty in it, but there's an abstraction. And then the actions are not going to be raw, torques going to the motors. It's going to be commands to some feedback policy that turns the high-level commands into actions. So this can also be problematic. It's much better at generalization. But it's still problematic. And so what we're going to do is we're also going to add a hierarchical planning and execution setup in which we have a close loop of replanning in order to do the planning and execution in the world. So basically, now we've gotten to the point in which this particular architecture is the one that I will be elaborating on, and which will be the basis of the systems that we're going to try to build. At least what preceded was a kind of justification for this particular architecture as opposed to some others which might look simpler. Okay, so now let's go back to our diagram here and consider how to approach different problems at different ends of the spectrum. So if the problem is narrowly specified, well specified, and we know a lot about the domain, we can do classic engineering and achieve marvels. We can get fighter jets. We can get Atlas doing parkour. In a rather narrow, well-specified domain. In this particular situation, Atlas knows exactly the heights of all of the boxes and so on, and it's amazing that it can do that. But it's it's narrow, and we know a lot about the problem. So that's kind of a baseline, and that's important to know. One of the things that's happened recently is that it's another approach to handling problems which fit into this area is the idea of neurodynamic programming. That's what Tsitsiklis and Bertsikas used to call it. You can think of it as reinforcement learning and simulation. The AI hand manipulating a Rubik's Cube is a good example of that. It's a remarkable achievement in terms of control, but very narrow. In fact, let's kind of look at that problem, right? Because it's interesting to compare that approach to the kind of architecture that I kind of outlined later. So in the idea in this particular approach is to think of machine learning in this context as a compiler. Basically, what we're going to do in the factory is we're going to have a general purpose simulator, and we're going to go through a lot of loops of simulation to try to build a policy, a Q value or a policy, whatever, and to do the task. And so for many people, this has the appeal that it feels like you need to put in less work or less knowledge than in the classic formulation that I mentioned earlier. But let's look at that a little more closely. So this is the architecture that I talked about earlier, and let's look at what some of the pieces that might go into this are. So in both cases, you need to specify what you want. So in the RL case, that's specified by a reward function. And in some cases, in fact, in many cases, in order to deal with complicated problems, you need to make the reward be dense. And we'll look at that in a second. And on the right-hand side, we need to specify a goal. So in terms of dense reward, this is actually drawn from a particular suite of problems that RL problems. And this is the reward for a pick and place action. So in fact, it's basically a solution of the problem with some approximations, and it's okay. That's what you're using to reward the object. But I mean, some poor graduate students spent a long time doing this, so it's not like it was free to train the RL on this problem. Some engineer had to work. On the contrast, for these kind of high-level planners, the goal corresponding to that situation is very simple to specify. That's the kind of big plus here. And you can specify many goals in many environments very simply and expect generalization. The other thing you need is you say, well, okay, in order to do plan, we need a URDF, we need a description of the world. It's important to remember that on the left side, you also need a URDF because it has to go in the simulator, right? So you need to be able to simulate the world well enough in order to learn from it. Now there's other approaches that we'll talk about later, but in this kind of RL in the factory, this one has to build a simulator. And then the physics has to be specified. Now, if you're using standard physics, like, if you can get to use Majorca or PyBullet or something, then the physics, somebody else did it, but somebody else had to do it. I mean, it was not, it didn't come for free. If you wanted, we were looking at a project in which we wanted to look at magnetism. And the question was, well, can we simulate magnetism in our simulator? And it's not so easy. Okay, so here is where I think the big difference comes in between the two approaches. So over on the left, you build a simulator. Over on the right, a simulator is not good enough. You need to do some additional work. So, and the additional work will be, in our case, by the way, I'm going to mostly talk about the type of TAMP planners that we've built. So, there are differences between different approaches. But basically what we need is operators, we need controllers, and we need a set of features for a language for describing the world. So let's keep that in mind, because that is really where the effort comes in in this particular approach. Okay. So we've looked at this corner now, the RL in simulation or classic engineering. What I want to talk about now is finally TAMP, and I ended up, which I believe sits in this place in the spectrum. So it's able to deal with a wider variety of problems, tasks, and it can generalize over goals very well. There's this issue about where the controllers come from and the language and so on, but I think the basic technology allows for having simultaneously and incrementally an accumulation of the kind of knowledge you need to build a new domain. So as Chris said in the introduction, the key idea in task and motion planning is that we want to plan for achieving a goal, and we want to go from the high level objective all the way to the robot control. And we have to deal with continuous metric spaces, very high dimensional, which is the area where sample-based planners excel. And then also have a representation of the dynamics, which are factorable, which can be used, which can be exploited by high-level planners to get very efficient, long horizon planning. So the goal here is to try to get the best of both worlds in one system. Okay, so this is a reminder of the kind of architecture we're talking about. I'm going to be talking about the planner primarily now. Later, once we start looking at applications that happen in the real world, we'll also have to talk about perception, execution, and control. But that will happen a little later. So I'll focus on the planner first. Now, as I said, the key issue, the key value in this approach comes from the abstraction. So if you think about a raw simulator and you're thinking about, incremental joint torques and displacements with a horizon of, thousands of time steps in order to, control the mapping from actions from perception to torque, you're basically hosed. I mean, there's, the idea of kind of looking ahead to the, to do a long horizon, planning is I think, very hard. Not to say hopeless. Okay, so instead, the idea in these task and motion planners is to operate on an abstract model where the action space is lifted in the sense that it's independent of the particular objects you're dealing with, and compositional, so that you can add new capabilities. Now, for planning, the kind of horizon that we can really do is maybe 10, 20 kind of steps of look ahead in order to be able to do it in a reasonable time. And this is a place where if you can do things hierarchically, really helps. And one of the important things about these methods is that they're search-based, and having a heuristic is essential. And one of the key advantages of using AI planners is that one of the great ideas of all time is the idea that you can construct domain-independent heuristics to do searching. Using the AI planners, you get to exploit that. So the important thing about these abstractions is that they make the problem easier. You have to figure out where to get them, but the problem is easier. The solution quality is not much worse, and you can solve the problems that you care about. So what's an example of this abstraction? So at a very loose level, the idea is, okay, let's think about pick, an operation of picking an object from a pose in a grasp with a particular robot configurations. Now, we're going to assume that the parameters such as pose and grasp and configuration are continuous high-dimensional parameters. There is no a priori discretization that we're going to assume. Everything is, continuous, because if you're going to deal with the real-world inputs, it's going to need to be continuous. And then there's a set of preconditions which are specified, which is basically specified in a vocabulary, which is relational. It says relationships among objects, and also identifies what the key state variables are. There are also effects that are specified in that same language. The idea of preconditions and effects is essential in order to break down the problem and be able to do chaining, so that you can figure out, you can think about what you're going to do in order to achieve something else, and so on. So it gives you that recursive ability. The other thing that we need is okay. We need a pick controller. We need a policy, a closed feedback loop policy, usually parameterized, which is going to be called once we have found the parameters that are necessary for doing the task. And as we'll see in a minute, we also need samplers. That is, our approach is going to be sample-based. At this high level, and we need ways of, for example, sampling grasps or sampling kinematic solutions for the robot. So this sampling is an important part of the problem, and it's one way to think about it is analogous to the role of sampling in traditional motion planning. So if you think of a PRM in which one samples a set of configurations of the robot and connects them with possible paths, and then searches the graph. The strategy we're going to use for task and motion planning is quite similar. We're going to sample grasps, configurations, possible paths, and we're going to then connect those using the AI planner. The samplers that we'll use are conditional, meaning that the values that they sample depend on each other. So for example, when you do the inverse kinematics, the sampler depends on a pose on a grasp, and then it samples a configuration. And the part of solving the problem is actually finding a way of connecting these samplers so that you can, for example, to get a trajectory, which is what a motion planner gives you. That's a sampling method for getting a trajectory. You need a configuration of the robot. To get that, you need the inverse kinematics, and for that, you get that from the pose of the robot. So by having a set of these basic samplers, the planner has to connect them up in order to construct a working program. The approach of Fiddlestream, which was developed by one of our students, Kaylin Garrett, basically operates by constructing a set of samples such that when plugged into these abstract operators, produces a plan that's consistent, that satisfies all the constraints from the initial state to the goal state. So what you do is you sample values and then try to generate to see whether there's a plan that is ground in which you have substituted the values, and see whether a plan can be constructed. But rather than doing it blindly, the algorithm actually uses partial plans that were built with insufficient samples to guide where additional samples are needed. So I don't have time to go into details on algorithms, but the basic idea to have in the back of your head is it's like sampling-based motion planning one level up, in which one has there are the discrete instances of the actions, which are the ones that need to be connected in order to construct a plan. That's the kind of high-level idea. So the key advantages of this kind of approach is it's modular, it's domain independent. We need these factored, abstract action models, and we'll talk about that later. We can encode domains with infinitely many actions by doing sampling, and we need those conditional samplers. And we can leverage the existing AI planners as black boxes to do the search in the system. So with that, putting all those pieces together, you can solve problems that are quite long horizon, involving kind of hundreds of actions. This, it's an effective strategy. What I'm going to do is pause now for questions and then talk about some of the kind of extensions to this basic paradigm that we have worked on. And then hopefully at the end, if they're having time, I'll talk about the role of learning in this process. Okay.
Let's open it up to the front row guests for questions.
I have a question. Yes, Tomas, I like very much your presentation and this way of presenting things. Which gives really, I think, a deep and at the same time view of the problem. But you mentioned that for me is key. If you can elaborate on it, you mentioned the fact that abstraction is key here in this task and motion, and I would say. I absolutely agree on this. And more than that, it seems to me that you need a kind of process which implement the abstraction online when solving the problem. Okay, going back and forth from the detail to the high level and back again while solving the problem. Do you think this is?
Yeah, there's different ways of thinking about that. I can tell you a couple of the ones that we've kind of thought of. So one way that this happens with us is that we have a hierarchical planner. So the way that works is that we drop preconditions in the to create abstractions, which can then be solved, and then then you try to refine it in more detail. So basically, you can create a set of sub goals by finding an abstract plan. So that's one kind of way. So I agree that there's these abstractions, in terms of time and space and so on, that could be beneficial in terms of solving the problems. Another things that we've been looking at is the idea of adding constraints. So one of the things that you can do is you can say, okay, can I solve the problem with only a subset of the objects, or can I solve the problem with only a subset of the rooms in the house, and add them back if I can't. So one way of thinking about it is that we only have a very small brain, so we actually have to turn big problems into small problems so we can solve them. So I think the idea of scaling algorithms is all wrong. We have to scale problems, but down. Anyway.
Yeah, plus the intricacies, I would say.
Yes.
Yeah.
Other questions?
I'd like to ask a question. Thanks very much for the overview so far. I mean, it's very, very clear presentation for things that I know are very difficult from thinking about it for so many years. So I'm curious about your thoughts on optimality versus feasibility, and in the quest for doing optimal feedback kinds of things. At the other side, we see that very simple random kind of motions or ergodic behaviors, things like this, have the ability to accomplish a lot without really knowing very much or doing very simple kinds of things. I was wondering what the role of those kinds of behaviors might be when sort of interleaved with trying to find the right levels of abstraction.
Okay, so you said two things there. So one is, what's the role of optimality? And the other one is this idea of there being I think of it as little policies that could actually solve the problem without the appearance of planning. I think that's what I heard you say.
Yeah, I guess it's sort of like these policies that are very simple may deviate away from optimal behavior, but then may be able to accomplish a lot in the process of doing that.
So I'm not a fan of optimal. Okay, let's see. I understand there are situations in which optimality is essential, important, but I haven't. Let's see. I think the only time I've ever worked on a optimal algorithm was in 1977 on the visibility graph algorithm. I think that's optimal by some criteria. After 1977, I gave up on optimality. That's not, I don't believe it's a critical factor. I'm more interested in solving bigger, harder problems. I will use, everything we do pretty much is greedy at some level. Now, I think the real challenge is how do you kind of make sure that you get reasonable solutions, not horrible solutions? So that I think is a real challenge. So, but I don't have a formal way of really addressing that, right? So I joke to the students, and pardon my language, that what I really care about is probably does not suck as the criterion for the algorithm. You know, it's like probably approximately correct in machine learning. That's roughly what I'm going for, because anyway, the problems are hard enough without making them artificially harder. That's just my personal view.
Thanks.
Any other questions?
I do have a question a little bit. So I'm interested in the representations that you have for the abstraction. So it seems to me, once we go into the abstract level, the representation changes substantially compared to the motion planning level, for instance. I'm wondering if there's something that is less of such a jump in the representation, because, for instance, there are hierarchical methods in motion planning where they try to represent things perhaps with regions, but it's still sort of sets of real numbers, for instance.
Okay, so it's important to understand that the abstractions that we use have real numbers in them too. So there's an attempt. If you go back to the origin of, okay, so what is the first task and motion planner? Shaky, right? Shaky had a motion planner, it had a task planner, and it solved the problem by finding a plan and then implementing it, at the low level. And but Shaky's abstractions were purely discrete. There were no real numbers in there, whereas our abstractions do have that. So they're in some sense intermediate. Where good abstractions come from is, I think, still the biggest open research area that I think for us. We're working on trying to find learning-based ways of discovering abstractions. But we did some work with George Conadaris when he was our postdoc, and on this idea of skills to symbols. And the idea is George's idea, it was that if you know the actions, then the symbols, the abstractions come out, are determined. And that is because you need to describe the conditions under which an action is applicable and the effects that it has. So you can, in principle, learn classifiers that describe states of the world under which the conditions under which the action is applicable. So if you have the actions, if the actions are given, then many of the kind of high-level descriptions, the symbols, if you will, can be deduced. Then, of course, you turn around and you say, where do the actions come from? And there are ways of trying to do it. George has some ways of trying to discover the actions. But the fact is that these two aspects of the problem, the kind of abstract representations, the symbolic representations, and the actions are really intertwined. the set of representations that you need depend on the actions that you have and vice versa. Because you want actions that will change the discrete values of your abstractions.
Very interesting questions. Let's go ahead and continue on with the rest of the talk.
Oh, I have more to, oh, sorry, yeah, go ahead. I will go ahead. Okay, so let me see. I ended up, okay, so this is a little bit lighthearted aspect. In the United States, there's a show called Mythbusters, in which a couple guys go around and try to kind of check myths and to see whether they're true or false. So I thought I'd take imitate them and talk about some TAMP myths and misconceptions, because they're, I find them widespread in papers that I read. So one of the most common ones is the idea that TAMP is task planning followed by motion planning, which is in fact a shaky strategy. But the fact is that doesn't work, at least not generally. Because the geometry in some sense impacts and in some cases defines the task. So in the little kind of example that the robot was solving here, there is no task plan that makes sense independent of the geometry. So really what one needs to do is one needs to combine, it's basically a constraint system that gets defined, which relates the state variables in the problem and a set of constraints that govern the changing of these constraints. And any reasonable task planner needs to intertwine the reasoning about the geometry and the task. So the idea that you can just kind of do the task planning and then do the motion planning, is not general. I must admit that when I was doing my master's thesis in 1976, that's what I thought their answer was, inspired by shaky. But since then, Rashid talked us out of that. So we really need to intertwine them. So following the outline of this show, we say that particular idea is busted. Okay. I'm having trouble advancing. Okay, so the other myth is that TAMP is only for pick and place. Now, in fact, many of the examples that we have seen are really pick and place tasks, but that's by no means the only thing. So let me try to illustrate some other examples from some of the recent work in our labs. This is work by Rachel Holliday, who's a student that Alberto Rodriguez and I co-supervise. So the idea here is that we want to plan to do forceful manipulation. So for the example here is opening a child-proof cap, which has to be pushed down and rotated in order to open. The basic idea is that in addition to the purely geometric constraints, collisions and so on, there are force constraints that have to do with the joint torques, and in particular the frictional joints that get created. But when you hold the tool or when you're trying to twist the cap and so on. So Rachel was able to address this problem within the context of Fiddlestream, and let me show you a couple of the examples. So the idea is that there are many ways of doing such a task, and you want to specify it so that the robot can pick the best way of doing it. One of the constraints is that you need to be able to resist the rotation force with, for example, friction from that red pad, or it could be from using a vise. You could turn the cap by holding it with the fingers. You could turn the cap by in this one, this one is moving it to the red surface because the friction coefficient is not high enough to resist the turning on the regular surface. And finally, at the end, we'll see it open the cap by using a high friction surface on the side of the palm. turn it around. Now, the idea here is that, in fact, this was specified as, let's take the cap off, and the robot can exhibit the different behaviors depending on the parameters that we know about the task. In this case, the friction coefficients and so on were specified. It wasn't doing experiments or anything. But the combination of searching over the strategies and the motions happen within the context of the task and motion planner. Another kind of example is some work that Kaylin Garrett and a student from the architecture department at MIT did on doing the 3D extrusions. This is a Klein bottle. So this was, the motions of this were planned based on a design, and you have to make sure that things don't fall down when you put them there, and that the structure can be supported and so on. So this is also built within the pedal stream framework, but very far from pick and place. So I will say that I'm having trouble with my, okay. I'm getting a real delay when I click. Okay, so no, it's not pick and place. It is limited by whatever domain you specify, but a broad range of domains can be addressed. Then there's the idea that, in some sense, that TAMP is really for deterministic and observable domains. And this is something that we worked on for a long time ago, is the idea that you can address uncertainty, in particular uncertainty in the poses and configurations of the robot, by having your state estimator construct a belief, which is a probability distribution over the states of the world, and then do action selection within the context of that belief. So we built a system that used perception, that it used a neural net based thing to try to get the locations of some of the objects and the classes, and then did some estimation of surfaces, and so that it would construct the locations of some known objects in the world. This is an old video that we did of the robot was asked to put the blue box in some location, and then had to move the object out of the way. And here it decided that in order to push, it can't pick up that object, it has to push it. So it has to move the obstacle out of the way, and the pushing doesn't work very reliably. So it does replanning after observing that it doesn't work. And in here it was asked to move out of the room, and it finds the chairs in the way and decides to move them out, and plans for all the motions. Now, there's no learning here. Only Leslie and I learned something from doing this, but there was no learning. This is Kaylin Garrett, working at NVIDIA one summer, did another belief space planner based on pedal stream. And the idea here is that it wants to make sure that the spam is in that second drawer. So it opened the first drawer, didn't see the spam there. Then this probability distribution about where the spam could be included the first drawer, so it had to open the drawer to find the spam, then put it back, and so on. Now this was all specified by a high-level goal that the spam be in the second drawer, that they believe with high probability that the spam is in the second drawer. So this shows that, in fact, it's effective to reason in the presence of substantial partial observability using basically a TAMP type system. Okay, that was the second piece, and then the third piece will be about the role of learning. Any questions now?
Yeah, we can take 1 or 2 questions. And Tomas, maybe you can stop sharing screen so we can see the videos of the front row participants.
Okay.
Okay, questions.
They're speechless.
Make a comment, right? I thought the PDL stream, for example, does emphasize optimality. Is that true, or?
You can run the planner in optimal mode or not. Stream is built on top of fast downward, and fast downward, if you assign costs to the actions, will try to give you an optimal plan. We almost always run it in greedy mode. You can solve longer problems predictably.
Yeah, of course. Sometimes, right? Sometimes it does help, right? This is a kind of more like a comment. I also like to hear what you think about. I mean, again, the talk is very interesting. I'm just focusing on the question a little bit here. So the sometimes optimality does help, like make plan actually shorter, right? So I don't know whether that kind of plays a role. Another question, let me just ask at the same time, is that this is somewhat related to when you I think Hannah's question, when you commit to certain motion, right, abstraction and the kind of task abstraction, right, we kind of are ignoring the underlying structure, right, a little bit, right? Sometimes, of course, you can argue that search is a one-size-fits-all approach, but that kind of ignores, for example, sometimes when you have like pick and place tasks, there's also some underlying structures, right? When you commit this, right, you're kind of ignoring this sort of structure. I don't know what have you thought about, when you plan this, when you develop this general planner, are you ignoring some other very important aspects of problems, right, that you're
Yes. Yes, and it's the trade-off that I'm willing to make. But your mileage may vary. You can choose something different. But I'd rather solve a larger. I mean, yes, when you introduce abstraction, you lose the idea of optimality. You can kind of pick an abstraction that's not too bad, but frankly, that doesn't bother me. If I can solve a bigger problem, I'm happier.
Yeah, I'm not fixated on either way, right? I do believe, as you said, right, we want to solve a problem, then think about maybe that's a very natural thing to do. I just thought, right?
No, I know you're absolutely right, and I mean I have nothing against other people pursuing optimality. It has a big role in the world, and I'd rather optimal control for aircraft is like a good thing. I'm all for that. I just don't want to work on that, but yes.
Okay, if there are more questions, let's save them for the final Q&A session. So Tomas, maybe you can go ahead and share the screen again.
So should I go then?
Yes, please.
Okay. All right, so this is where we left our problem here. We were kind of stuck in the low, on the x-axis here, assuming that we know a lot about the problem. So the question is, okay, how do we go up? So how do we deal with situations in which we might not know everything about the problem? So one answer that comes to mind is RL in the wild. I mean, you can do reinforcement learning in the wild. I mean, there are some obvious problems with this idea. I mean, I do not want the robot to be learning in my kitchen, when I ask it to make tea. So I'm just going to leave this out of the picture for now. Instead, what I'd like to do is to talk about how do we integrate learning into TAMP, in particular, how to exploit the fact that the TAMP representations are composable so that we can do continual composable learning within TAMP. So this was our architecture, and we've identified certain pieces of this architecture. There's controllers, the basic pick and place or whatever it is you're doing. There's perception, object segmenters, and simple shape matching. There's planning, operators, models for basic controllers, and so on. So, you can think of these as being models that are being used by general purpose algorithms. And so let's think about, there's also search control, but let's look at some of these pieces and say, well, can learning help us to acquire these and to be able to extend our domain. So let's look at the perceptions side. So this is a problem thing that we've been doing recently, partly to prove a point, but this is called MOM. It's actually M0M, so it's manipulation with zero models. So the idea is we believe in objects and assuming them to be rigid, and we know the robokinematics and so on. And what we're going to try to do is try to do TAMP without any prior 3D models, just driven by perception. And we're going to use, standard methods from the vision literature and the robotics literature to do class agnostic segmentation. So dividing up point clouds into pieces without knowing the classes there. We're going to try out some grasping methods that operate directly on point clouds that are based on learning. We're going to try shape completion for point clouds based on learning. And we're going to use that in the context of task and motion planning. The key insight is the following. So the connection between the model of the world and the planner are these samplers. For example, sampling locations to place objects, sampling grasps, sampling motions, and so on. And the samplers can get by, in most cases, with partial models. They don't need a one coherent, giant, perfect scene in 3D in order to work. So a placement sampler given a point cloud only, can use a convex hull and define some possible stable surfaces and then fit planes to find places to put things. The grasp sampler can use one of these trained methods that work directly from point clouds. The motion planner for collision checking can use the approximate volumes by doing shape completion. So each of these samplers can operate close from input that's closer to the raw data than from the abstract perfect 3D model. So we can try to do that, and we can use segmentation. This is the examples, of segmentation of some scenes using UIS is an existing segmenter system. And if you look at it closely, that we're not going to have time to do, you can see that it actually kind of has some of the right ideas. There are mistakes in it, but it's enough to be useful. And so that you can, for example, take that image on the left and construct the image on the right, which is, if you take the point cloud, if you only use the point cloud points, you get a very partial representation. If you take the convex hull, it tends to leave out any non-convexities and so on. In fact, what we actually do is actually use a concave hull algorithm, something derived from alpha shapes. And the result is that it produces partial models that the samplers can operate on. These kinds of meshes we use primarily for collision checking. For grasping, we can operate more directly on the point cloud. But basically what we've set up now is a very simple method that basically does closed loop using most likely state. This is not the right way to do this. The right way to do it is actually to do a belief space planner based on a belief space distribution of the input. But so what we've been doing is we do the post estimation, get these kind of partial models. We take a goal, which is specified as a kind of a first order logic kind of statement about what the objects are in regions. In order to prove a point that we don't have any classes, a lot of the goals involve color. So put all the blue objects in the green region and so on, just as having a way that's directly accessible. Normally, you would actually want to recognize some things and give them names and so on. But anyway, that goes into the motion plan, the task and motion planner, which produces a plan which we execute. Then we look again and see what happened, and we repeat. So that's basically, it's very simple strategy. So what I'm going, Kaylin here is setting up this. The goal here was put all the fruit in a bowl of the closest color. So it's, you know, it's doing the detection, segmentations, grasping, and then, you know, operating on each of these objects without any models. Here's another one in which, okay, so now it can't see the two objects that were closer to you. So it moved the box over. The goal is to put everything in the blue area. So then it saw two objects which weren't in the blue area and then moved them to the blue area and then finished off its goal. Again, there are no models. It's just doing things based on its perception. Here, the goal is to put the mustard bottle. In this case, it knows about the mustard bottle, and it has to move stuff out of the way. You know, it had a bad grasp to start off with and got a good one and did its job. This is one of my favorite. It's a failure, but it's an interesting failure. Okay, so the goal was to put this Lego object in the blue area, okay? So it goes, picks a grasp, and oops, the object fell apart. So it looks again, you say, okay, I can do that. Oh, the object fell apart and it fell out of the box. Then it missed. So it goes and replans and, okay, this guy's not in the blue area, let's put him back and then pick up the base and put it there. So the important thing about this is it's doing its planning. It's doing, you know, kind of long-term planning based on the information that it has, and you get you know, interesting behavior, and there's no learning going on here. It's generalizing based on its domain model, which is mostly a pick and place operation. We've done a lot of these. It's very easy to set up cases, and we've done a lot of them. The only limitation has been the limited access to the robot during the pandemic. But all right, so that was, you know, there's learning perception and using it within the planning system. Then the other area that's of interest is learning operators, which is one of the kind of big issues. I'm running late. Should I stop?
No, we can continue on for a little bit more. We have
okay, I'll try
25 minutes for questions.
I'll try breeze through. Okay, so how can you learn operators? What we're interested in is how can you add an operator to a system that already knows how to do stuff, rather than how to start from scratch. So there's been a tremendous amount of work on learning skills over the years. People have worked on this. The question is, how can we add a skill to an existing set of skills that's composable, and that's been our focus in this work. The idea is that if we get a skill which has some parameter, for example, imagine that you had something that was a gain, you can construct an operator in which the skill is pouring, which has a gain, and it produces some result. And it has a set of preconditions which introduce variables into the problem, like which grasp you're using and the width and the height of the object and so on. So the other thing that the operator has is a constraint which involves all those variables. In order for the skill to succeed, it needs to, those variables have to have a relationship to each other in order for it to succeed. And we learned that by using Gaussian process regression. The nice thing about doing Gaussian process regression is the fact that you get uncertainty. So you can do active learning to get the examples that will give you the most information. So that's what we do for learning. The things that, okay, there are details that you can read about. One of the things that I wanted to emphasize, however, is in order to, gathering the data is very hard, but it's essential in order to get something that actually works in practice. One of the things that we do in order to gather the data is we use the planner itself in order to do most of the motions. So, picking up the cups and moving into the right position and so on are all done with the planner. This is the planner training. This is a training case. Here are some examples of learned pours after it's trained. And here are some learned scoops, which is much harder to do, especially with overfull bowls. but it manages to learn the task. And the important thing is that once you have that kind of description of the task, that abstract description of the operator gives you, you can combine them with the other skills, like the pick and place skills, in order to do complicated tasks. You can bring the bowl to a place where you can pour, for example, because you understand the relationship of where the things have to be in order for the pour to succeed. And so all of this, can be done in one system. And now, if you want to add pushing and you want to add cutting and so on, you can put it all in the same framework, and it works. This is another project that we've done recently, which involves learning a global constraint on the state. So, for example, if you want to stack blocks, these are weird blocks with sorry, my block that have weights in weird places so that they're very hard to stack. The robot knows where they are, but it's actually hard to model the conditions under which it succeeds. So what we've done is set up the robot as an experimenter. So it kind of builds these stacks, learns from them, and then cleans up after itself. So this is using the pillow stream framework to do the learning infrastructure. And the result is actually, if you look at this, that if you use analytical models or simulated models of the stability, they don't quite work as well as the ones that were learned from the robot experiments. The robot was built 400 towers over a period of 55 hours of continuous operation. So, and it learned from that a model, a kind of more global model of the system. Now, we can also learn how to make the planning faster by learning Q functions at the abstract level. I don't have time to talk about that, so I'll skip this. It works and so on. So there's a lot of other stuff to do. In particular, this issue about learning where the abstractions come from. But I guess what I've been trying to push is the idea that if you care about general purpose robots, it's very important to pick methods that have properties that lead to generalization over goals, generalization over environments. And that this is what will enable us to attack complicated problems that involve a variety of environments and a variety of tasks. All right, well, thank you for your attention, and sorry that I ran over.
Thank you so much, Tomas. That was a fantastic talk. I think everyone will give you a virtual round of applause. Let's go ahead and start with some questions from the front row, and then I'll proceed to some of the questions on Slido.
Yeah, I'm curious about one thing. So with respect to the failure cases, can you talk a little bit about perhaps different types of failures and how that would affect the performance and capability of the robot? Because I can imagine, for instance, if the failure is it drops ceramic, for instance, and it breaks, it might be a bit more difficult to recover from compared to other.
Oh, absolutely. And we're nowhere near dealing with anything that complicated. The idea that a single object becomes many and you have to pick them up and so on. I mean, I think we could, if that became an important issue, I think we could imagine how to approach it. But so there's the idea of an irreversible failure, right? And there's the idea of a reversible failure. So this system, like the one without models, is just a simple loop, right? It's just saying, try something, then look to see whether the goal was achieved, otherwise try again. That's not the right way to do things. The kind of belief space planner that I showed you earlier, which dealt with uncertainty over the poses and configurations, could be extended to deal with uncertainty about shapes and so on. And then it could do active data gathering to find out, the information that it needs to know. And one of the things, at least the way we try to, one of the planners that we built When we build a plan, we characterize the precondition, the pre-image of each of the steps of the plan. So that's a set of conditions under which the subsequent plan is expected to achieve its result. So that leads to execution monitoring, because if the state is not in the pre-image of the rest of the plan, that means something went wrong and you need to replan. So it's a nice way of incorporating the kind of failure conditions that without having to explicitly program for them. But you know, ultimately, if the result of the failure is catastrophic, then yeah, we should program our robot to use both hands to go, huh?
Let's see. Tomas, would you mind stopping the screen share? Okay, great. We'll see all of our nice smiling faces now. Let me ask one question before we get onto the other front row guests. Let me ask one from Rashid. Do you have a follow-up?
I just a comment. I would like to Tomas to comment on it. In the last example, as you have shown, which are very interesting, can we say that your systems here or planners are exploring the physics of the actions, and then they use this for doing better sampling for performing that task? Is there some kind of exploring the physics, kind of naive physics?
Well, it's not naive, but
a little simple.
Okay, so it's part of a bigger project jointly done with Nick Roy and some of his students and ours. And it's called curiosity-based feasibility. So the question is, what's the criterion that you use for driving the search for particular examples, and its information, theoretic criterion for driving the search. It's not currently built within the planner. This is something that we could do. At the moment, we have an outer search to optimize the acquisition of the next example. It uses the planner as the low-level control. I want to put this object there, or I want to put that object there, and it uses the planner for that. Ultimately, you could imagine, a nice belief space, planner that actually did this. So if you think about uncertainty about poses, configurations, shapes, and physics, that would be the natural outcome. It would be something that would explore in an intelligent way to acquire data that it could use for planning. Yes, that's where we're going. There's a finite number of hands to.
Yeah, very interesting.
All right, let me ask a question from Slido. So the top question is, are there reliable design rules of abstraction?
No. Okay. So the closest thing to a design tool for abstraction is George Conadaris's approach. The limitation, the initial work that he did with us was for the propositional case, not the lifted case. So you really do want the lifted case. You want to learn operators that are independent of particular objects. So George has been doing some additional work to try to do object-oriented, agent-centric operations as a way of trying to do some of this lifting. We're also working on that. It is very much a research area, and I think an interesting and important one. But right now, it's the most reliable design methodology is to think about it and stare at a wall for a little bit.
Very interesting. I guess a similar, related question coming up is, can you comment on how to extend the methods to generating plans from both arms in the case of the PR2 or multiple robots and end effectors?
We do both arms in the sense of, they can use the right or the left hand. That's trivial. Doing motions that are joint is not trivial, but it's a well-known problem. You know, there are motion planners that can do that. You know, closed loop kinematic chain planning. We don't have one in our system, so we don't do that. It's not a big deal. So that's, you know, multiple robots. If you do centralized planning of multiple robots, that's just one big robot, and it's, you know, more complexity, but in principle you can do that. Kaylin has done some work with doing some simple coordination among robots. There are some standard PDDL domains that do multiple robots and so on, and so you can apply that directly. It's not clever algorithms for multiple robots like the stuff that JJ Jingjing works on. It's, you know, simple-minded stuff, but it extends straightforwardly, I would say.
But have you worked on any kind of, I guess, parallel planning where you can do one thing with one arm and another with another arm faster than thinking of it as
can we walk and chew gum at the same time? No. I mean, let's see. One of the things that we don't have and should have is some idea of time. So once you start doing a lot of stacking of operations, and you have to kind of introduce time. Time really should be in there because you need to worry about external events that have their own dynamics and time. So it should be in there. There are techniques in the planning literature for dealing with time. Kaylin has tried to use some of the time-based planners and for in some extensions of BuildStream. It's in principle possible. One of the big limitations is the fact that PDDL is PDDL is a standard, which means that there are many versions of it. You know, no two planners support the same standard. So it's very hard, and you know, it's particularly true for the time-based planner. So it's been a little bit of a challenge to do that. I think incorporating time in an intelligent way in these systems is an important other direction to go.
Okay, other questions from the front row?
They're so quiet. They're either bored or just stunned.
I can ask a lot, but I didn't want to ask always.
I mean, this is not directly related. It seems like the PR2 is a very good robot, right?
The PR2 is a fantastic robot. It's one of my saddest days was when Willow Garage went out of business. I mean, I tell people, okay, so you know, since we have time, I'll tell old person stories. In the you know, back when I started trying to do motion planning and trying to sell it to people in the you know, late 70s, early 80s, usually the only reaction that I ever got from anyone was, oh, that's too slow. I'm not interested in that. So, excuse me. So I eventually kind of gave up and said, bah, and I went off to do computational biology and, you know, and machine learning. And you know, 10 years later, I kind of got interested again because there seemed to be stuff happening in the field. And I came back to do robotics. And the thing that I remember very clearly is the day that the PR2 arrived in the lab. It was in this big box, and we opened it up and drove it out of the box. And I remember thinking, this is transformational. I mean, this is amazing. Now, I used to always say, the reason we don't have good robots is because of the robot hardware guys. They really can't do anything. And, you know, the perception people, they're not smart enough and they don't, you know. So suddenly the PR2 came out and I said, darn, the reason we don't have robots at work is my fault. It's software. I mean, you know, this thing is amazing. And it's too bad that, you know, it has been hard to actually hit that high again after Willow Garage died. But I mean, it really changed the way. I mean, you can look at my publication history over a period of time. When the Peer 2 arrived, all of a sudden we could do amazing things. Well, not amazing, but at least interesting things. It really was a big change for us. Longer answer than we wanted, but there it goes.
I have, if we have time, I have another comment, Tomas, concerning. I think that this problem of task and motion planning is very rich because it is, and as you have shown, it can be extended not only for pick and place but for a large number of tasks. And in fact, it is one key aspect of the future intelligence of this kind of the robots. Okay, the ability to manipulate and to reason about things. And I think, so you mentioned the issue of multi-robot. I think for multi-robot is very important, but also for, I think it can open for interaction with humans. In order to approach a human, to give an object to a human, to choose how to do this. There are different ways of doing it. And it is also important to open these problems, this kind of reasoning for such kind of I would say, interaction or collaboration. And I think so it goes largely, as you mentioned, more than pick and place. Even I would say a robot doing observation could need this kind of reasoning, pushing an object to look behind, etc., reasoning, all this kind of thing. So I think it's really one of the difficult problems of today for robots. I think, I don't know if I'm sure you share this, but can you comment globally on this? What are the difficulties there, and where should we go?
That's a good question. Of course, you've done a lot of work in this area, which people should read if they haven't.
I want you are doing a lot of work.
Yeah, no, I mean, my philosophy is always to let other people do the hard problems. But anyway, no, you're right that that interaction with humans is an important aspect of robotics. I have always said that the level of intelligence or capability of the robot really affects the nature of the problem. So, for example, nobody wants to work with a human that's not very capable. Yeah. So no one wants to work with a robot that's very capable. Right. So I think a lot of work that focuses on how do people feel about dumb robots, it doesn't strike me as, oh, well, okay, maybe we should make the robot smarter and then people would like it better. So one of the things we've been trying to do is to try to make it smarter. But I mean, we have worked on the idea of interacting with humans, and the big issue, of course, is estimating the state of the human, which is very hard. We did a little bit of work in the context of PON-DPs for building non-playing characters in games, in which the idea was to try to estimate the goals of the player. So to try to pick goals for the robot to do that would be helpful. And we've done a number of things in that direction, trying to estimate the goals of humans. We work with Josh Tenenbaum at MIT, who's a cognitive scientist, and they've done some work on theory of mind as a way, using some PON-DP type ideas to try to do estimates of people's goals and desires, intentions, and so on. I think it's super important. We haven't prioritized it yet because we've been trying to make the robot smart or smarter, so that it would be easier to work with.
Yeah, but I think my point is, in order to make the robot smart, for example, even the handover, how to give an object to a human, this way or this way, or needs task and motion planning and reasoning. This is what I wanted to say, because if not, the robot will be too too, I would say, too strict in its use for the human if it is not able to
no, I mean, I agree completely.
Abstract.
Yeah,
Abstract somehow.
You know, at some
abstract the task. Yeah.
At some perhaps an interesting technical level, one can say that a lot of the challenges in task and motion planning are determining models of the world. Yeah. So how does the world work? And once you know how the world works, then you can act appropriately. Yeah. So humans are part of the world, and estimating what they're doing is part of the problem. You know, we've focused on the center of mass of objects and other kinds of simpler estimation problems. But I mean, ultimately, the limits of all of this is how well can we estimate the state of the world, and including the dynamics, the rules that govern the behavior of the world and the humans in it. So at a technical level, I could answer you, oh yeah, we're working on whatever you say, because that's what we're working on. How do we do the estimation and the planning based on the models that we get?
So we also have a similar question from Slido.
Yes?
I'm sorry, we have a comment from Slido asking you to comment on the role of tactile and force perception on tasks involving complex interactions with the physical world, which I think is quite related to what we've been discussing.
I mean, it's super important. Let's see, I got into robotics in 1974 because of a force assembly that Hiroshi Inoue did when he was at MIT visiting for a year. So it's always been close to my, dear and close to my heart. In the context of task and motion planning, it's another one of these. Okay, so you build feedback loops, which are the abstract actions, and then you plan in terms of them. And a very important set of feedback loops that one builds are, for example, compliance. The examples that you saw of, I showed of that Rachel did on turning the top of that bottle is done using compliant control, impedance control on the Panda. Choosing the parameters automatically for doing a task and so on. We have another PhD student who's working on that. So dealing with the world in the presence of uncertainty requires that the robot be compliant and or be able to sense. So this is something that is super important and something that we want to work on. I mean, we started working on that in 1982, but it's still important and not solved.
I have a question. So if you could take over, let's say, a big company like NVIDIA and make them work on whatever special purpose computation device for the next 5 years that would help robotics or help some of the kind of things you're doing, do you have any idea what kind of architecture you might propose? Because you've seen, as you mentioned early, when you planted the seeds for motion planning, you went away because it was too hard. Then time to come back. The CPUs are powerful enough, sampling-based motion planning kinds of things work. We see the same thing with deep learning. There's people discovered, oh, look, GPUs can make neural nets work now with more layers and more nodes. And now it's powerful enough to solve some problems with enough data and things like that. So is there some sort of next architecture that might be within reach within a few years, if only one would invest a few $1 billion into maybe developing it over several years?
That's an interesting question. I mean, there are a couple of things that come to mind. So not to pick on George Conadaris again, but he started a company to do real-time motion planning and exploiting hardware, and it works very well for limited, for kind of industrial tasks. But that was a case in which one can turn the kind of collision checking based on depth data into a kind of nearly instantaneous planning in real time. So that was a very interesting case of hardware kind of taking that problem, which even though there's been tremendous progress on CPUs and GPUs for motion planning, it brings it down to some millisecond times, and it's like amazing instant. So that's an interesting case. I've spent some time trying to look at parallelism in in planning. And one of the drawbacks of the methods that at least we use is that they don't parallelize very well. So, I mean, it's an I think it's a very interesting question. I don't have particular insight, aside from, you know, this thing that back in the day when the connection machine came out, most of you are maybe perhaps too young. Is this early parallel machine? Pat O'Donnell and I built a parallel motion planner that used this, you know, think of it, it's kind of like a GPU. And that was kind of cool, but it was super hard, and I decided at that point I wasn't going to do parallel hardware anymore. But it's, I mean, you know, when I sit here, you know, I have 8 cores of my machine, and only 1 ever gets used, except when I run the C++ compiler, which uses every core for infinite amounts of time. So, I mean, I get jealous, like, gosh, I wish I could parallelize like the C++ compiler and run things faster. But.
So questions are coming in fast and furious online. I want to give us a couple of minutes just to get through some of these. One of them is, Tomas, you gave up on optimality. How about completeness? Are there any guarantees that a reasonable solution will be found?
I care more about completeness. The usual problem with completeness is stating what the criteria for completeness are. So it's very tricky in a general purpose, you know, AI planner and so on, to talk about completeness. You can talk about completeness of the underlying algorithm relative to the domain description, but it's not about it. You know, there's the leap from that to the actual problem. Will we solve any problem that we actually face? Because the kind of representation and abstraction gap from the real problem. So I care more about completeness. Of course, in practice, you know, things like asymptotic completeness don't help you because they don't have forever to run. But it is a habit of thought that I still cultivate, and I try to cultivate in students, is to ask, well, you know, what are you giving up in terms of completeness? It's a question you can ask about many of these planning systems. It's not a question you can ask about a deep learning solution. But I care more about completeness than I do optimality.
Mm-hmm. There's also a related question here where we reason about object constraints. Do you rely more on perception inputs or use algorithms like minimum constraint removal to get constraints?
Well, it's not an either or. I don't understand that. Let's see. Minimum constraint removal is super important. It's actually the version of motion planning that we actually use in our planners, because when we're doing backward chaining, that's the problem that comes up. It's minimum constraint removal, identifying the things that you need to solve next. We were doing it before Chris published his paper, but we learned from Chris a lot that you know, different algorithms and methods. But if you do backward chaining, you set up, you know, what you want to know is, what is it that's preventing me from reaching my goal? That's the question that you ask. So algorithmically, one relies on the, you know, those kinds of the answer to those questions to drive the search. The perception gives you constraints from the state. Ultimately, the solving a planning problem means connecting the hypothesized goal state to the current state. So you get the constraints that you get from your models being chained, and you need to connect them to your perception. So it's not either or, it's both. I mean, the way to think about these systems is a giant constraint satisfaction problem in continuous space. So all the constraints come in and interact.
Yeah, great. I'm going to do one more question here, and then we'll leave the final word to somebody on the panel who wants to have the last word. So the last one from Slido that I'll ask is, what do you see as the major blocks to develop systems of multiple robots, each less capable than a PR2, but capable of cooperating with each other?
The main loss? It was
major blocks.
Oh, blocks.
Challenges.
Okay, so roughly, if you're doing centralized control, I mean, that's just a different kinematics. And you would need a different abstraction. One of the things that we've benefited from humanoid type robots is the fact that there are a number of abstractions that you can intuit based on your own experience that are useful. So somebody asked earlier, where do abstractions come from? Well, many of them are just intuitions that you formalize. So I think that if you have something that is very non-humanoid robot, I mean, a very good non-humanoid robot is like a house with all kinds of automation or something. It's still, in terms of planning and so on, everything is cool. It's not different in some sense. What's different would be the set of abstractions that you need, I think. And so we probably don't have the right set for, if you have if I have a snake robot and some kind of other weird robot, and I want to put them together to do a task, I might not know where to start in terms of creating the right abstractions. Maybe that's a case in where machine learning would help.
Great, thank you very much. I think in the interest of time, I'll actually, unless somebody wants to interject with a final word, I'll give you a couple of seconds to think about that.
I have basically one question. It's a bit of speculation. Tomas, how would you say this all generalizes to more dynamic tasks? Since, I mean, if I look at all the videos and things we've talked about, these are quasi-static tasks. And what will happen to make a person who likes dynamics happy?
John, you're just out of luck. Sorry. I always I talk to Russ Tedrake, who has the same concerns, and I tell him, well, you do the freaky dynamics, I'll do the other stuff. Okay, so at one level, there's one answer within this framework, which is it's a different skill. As long as you give me a parameterized skills for juggling, I can make sure that the conditions that for that skill to be applicable are there. I can remove any obstructions. I can whatever. That would be what the planning. But the skill itself would be something that you've worked on how to learn. And for us, we would abstract away the fact that it's a parameterized skill. And then you can do dynamic tasks. There's another issue, of course, which is if you want, okay, there's what I would call an episodic dynamic tasks that has boundary conditions that are quasi-static. And there are a sequence of dynamic tasks. For example, if I throw a ball to move an object, right? So there was a dynamic task, dynamic motion to throw the ball, and then it hits the object and moves it. So there, the boundary conditions of that throwing motions are not quasi-static, and so now I have to represent the velocity of the ball and the box in the state. In principle, doable. Hasn't been our focus, as you said, but I mean, I think there are ways of attacking it.
Well, this has been a really great, all of the directions of conversation have been fantastic, and I've really enjoyed the talk and all the discussion from all the panelists and all the questions from the audience as well. Unfortunately, all good things must come to an end, so I'll just go ahead and thank Tomas and all of the front row guests again, and thank you all for coming and attending the IFRR Global Symposium. I will close by reminding you that in 2 weeks, we'll have another symposium on the exciting topic of flying on Mars. So hopefully you'll join us on June 10th for that. All right.
Thank you very much.
Okay.